Okay, today we're going to have a look at harder curves in 2 dimensions and 3-dimensional curves. So last lesson we saw a variety of different curves, but it's quite likely that you'll come across much harder curves, particularly late in the exam, and you have to sketch them. So for unknown curves, it can be helpful to work out a domain and range, and lightly draw a box on the number plane as a guide for your sketch. The second step is to create a table of values to sketch the part of the curve, and symmetry or just a bit of thinking can help us as well. So if we think of the domain and range of this curve, well, the domain, we're just looking at the x value. We don't care about the y because we're looking at domain at the moment and it's parameterized. So sine squared, well, the squared gets rid of all the negative parts of sine. So it's from 0 to 1 now, because 1 squared, the maximum is 1. But we're timesing it by 2, so the domain is from 0 to 2. And I like to draw that little sketch. The domain is from 0 to 2. And, well, cos is between -1 and 1. And since nothing's happening because there's no 2 here or there's no +1, it just means the range is from -1 to 1. So that's our thing there. Now, we know the maximum of this domain is 2, and we're really thinking to ourselves, I need to fill in this table of values, but what do I make my values of t? Do I go 0, pi, what do I do? Well, we're thinking of trig, so we're going to get nice and easy values if we do things with pi's in them. But we might think, oh, am I doing 0, pi, 2 pi, 3 pi? What am I doing? The best point of call is to consider what is your maximum in the domain. We know the minimum is going to be 0 radians, but the maximum is going to occur when x is 2. So let's make 2 equal to 2 sine squared of t. That means sine of t is equal to 1, and t is pi on 2. So the maximum is pi on 2. And we're just going to evenly divide each of these, so we can have some nice points. So we're just dividing those equally. If you do all of those, you get 0, 0, 1, 0.3, 0.9, 1, 0.7, 1.7, 0.4, and 2, 0. So let's just sketch that. So we've got 0, 0, it was 0, 1. We don't care about these t values anymore. We're doing x and y. So 0, 1, and then it looks like we're just going down. 1, 2, 3. And then we've got here, that's a 2. So I think the curve looks like that. Sadly, though, it's not that easy. We've got to consider the symmetry, or the symmetry of this graph, or we have to do a bit of thinking here. These are radians along the side, and they're radians in the first quadrant. Or not in the first quadrant, they're kind of positive radians. My first quadrant's up here, and the fourth quadrant's down here. And we know that cos has answers here and here that are both positive, because cos is positive here and positive here. So when cos is equal to, say, pi, let's say pi on 4, which is in here, cos could have an answer here, but it also would have a valid answer down here. So this curve is reflecting like that, and that's our answer there. The next thing we're going to have a look at is curves in 3 dimensions. Now, the parameterized curves in 2 dimensions that we've just looked at involve a point moving along the curve on just the xy plane. We can visualize this as a point moving along a piece of paper on a desk. The point will often follow a circle, a parabola, or ellipse, or a hyperbola, and we often call these points that are moving locus. For easier examples of parameterized curves in 3 dimensions, we can think of the point moving around the xy plane, but also rising and falling. This elevation is the z value. Often the point will be still forming a circle on the xy plane, but it could be an ellipse or a parabola just on the plane, but it's been moved up or down. The elevation will either be a multiple of a parameter so it will rise steadily, or a function, which means it rises and falls. If we want to make the question harder, we can make the point follow a regular shape in the xz or yz plane with a linear function in the equation x or y. If we get stuck, it can help to focus on only two of the parameters, using them to draw a top view, a front view, and a side view, like you would have done with solids in year 7. So, curves in three-dimensional space that aren't a sphere. This one is the easiest they're going to be, because this is simply a circle of radius 1, and its z value is 2, which just means it's a circle of radius 1 that's been moved up by 2. Simple. So a circle of radius 1, centre 0, 0. Well, the original centre without being moved up would be 0, 0. So circle, radius 1, and it's at 2. So the centre of this circle is 0, 0, 2. The next thing we're going to have a look at are helixes. So helixes are kind of like spirals, except we're increasing as well in the x direction instead of spirals being a 2D thing. Now helixes are kind of like a coil or a spring, or in biology you've got your double helix, which is your DNA. So a helix is when you've got x cos t, y is sin t, and then z is some constant, but it's a function, so it's increasing up or down. So if we have a go at drawing a table of values, which I've done for you, notice that z is equal to t, which means their values of t and z are going to be the same. So if we just go from 0 to 5 pi on 2. So the thing we first do with our helixes, and I will admit they are hard to draw, what we do with our helixes is we draw a Cartesian plane, and then we draw our z plane. And the thing that's best to do first, I might extend this a bit, and let's hope I can get this on the first go. I'm not the best at helixes. I'm going to make this x and this y and this z. The thing we do first is draw a big unit circle. So that's going to be 1, that would be minus 1. So, drawing our dotted lines. Now this, it's a circle on the x, y plane, so it's meant to look flat. Okay, then what I like to do next is change the colour of my pen and draw dotted lines along the kind of points on the circle, so 1, minus 1, 1 and 1. Draw those dotted lines. In an exam I do those in pencil. And notice that the reason I've drawn the dots there is because this is where it's rising and falling. We're seeing lots of zeros and ones. So forget about this for a second, because we're going to add this in last. What you will struggle with is if you plot these along the axis, along the z-axis, because these are our values of z, you're going to come into a lot of strife. So we're going to draw the spiral and then just add in those values last. So we've got x is 0, y is equal to x is 1, y is 0. So we're here. And then our next point, I'm going to draw in 2 points, and then I'm going to do the rest. Because it's a helix, it's going up in a spiral. We're here. So we're going from here up to here. Then we're going from here to here. Then we're going across to this one, and then up to that one, and then across to this one, and then over to that one, across, and so on like that. Okay. Then, I wish I could erase just blue. We're going to get rid of these. And we've got a helix. Again, I'm not saying this is easy to draw. These are not easy to draw. Before I made this video, it took me about 5 practice goes before I figured out how to do it. And that's our helix there. Then I would simply add in, we're going pi on 2 here. Then this is pi. Then this over here is 3 pi on 2. Then this here, which the next one is 2 pi. Then our next one was up here at 5 pi on 2. And we go on and on and on and on. That's the idea of helixes. We're going to practice lots of these, and it is quite tricky. And we're just getting the general shape and understand what's happening. So this is a coil and it's going up and up and up. Okay. One of the last things we're going to have a look at are unusual looking curves. The hardest types of curves, in my opinion, are these ones. And that is where, yes, it's a circle, but also what it's increasing and decreasing by is a function of t. So, well, not a function of t, it's a sine function or a cos function. So it's going up and down, and that's because sine repeats itself after its, what do we call it, period. It's periodical, it goes on and on and on and on. So it's not going to just keep increasing like the previous one was, and that's because z was t. Z just keeps getting larger and larger. But sine is in between -1 and 1, which means the maximum this graph is going to be is 1, and the minimum is, the maximum this t is going to be is 1 and -1, which means the z is just going to go up and down and up and down, and that's because z is between -1 and 1. Sine of 2t is between -1 and 1, so it's going up and down and up and down and up and down. So because the maximum is 1 and the minimum's -1, so it's going up and down and up and down, let's figure out those critical points. When is it 1 and when is it -1? If we solve sine of 2t is equal to 1, well, we get pi on 2 plus 2 pi to that because we go around twice, we get 5 pi on 2. Divided by 2, we get t's pi on 4 and 5 pi on 4. Same idea here, make it equal to -1, that's going straight down, 3 pi on 2 plus 2 pi, we get 7 pi on 2. So t is 3 pi on 4 and 7 pi on 4. So to do these types of questions, I like to look at our critical points because it's not going to follow the same pattern that we've seen in the previous ones. So here are some critical points. The other critical points we're going to look at are the points along a circle. So 0, 1, 0, 0, 1, -1, 0, and 0, -1. And we're going to make a table with those critical points there. So 0, 0, 0, 1, -1, 0, and 0, -1. Of course, we know from Year 11 Advanced radians that these would be, when our x is 0, we're at 0 radians or 2 pi radians. When x is 1 and y is 1, we're at pi on 2, pi and 3 pi on 2. And then let's fill in our other coordinates, those 4 critical points. So pi on 4, 5 pi on 4, 3 pi on 4, and 7 pi on 4. If we fill in all of that information into these 3 equations, we'll get this. And we're going to graph that. And it looks difficult, but it's not. It's just, the shape is scary, but it doesn't have to be perfect. We're just after the general shape. Do you know what's happening? Do you know that it's repeating itself because it's sinusoidal, or it's trigonometric, it's periodical, it's repeating itself, it's going on, it's not increasing forever. I like to make x down there when we're graphing these. It makes the helixes easier, so let's make that consistent and make these ones easier for us. So we're going to again draw in our unit circle. 1, that would be a -1 up there. make this a 1, that a minus 1. Oh, that's not the best, Tom. Okay, unit circle. Now, notice that at the 4 kind of endpoints on the circle, the 2 x is 0, y is 1, y is 0, and so on, they're all z is 0. So let's plot those in. Now I'm going to do it in green. Plot here, 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 and here. They're always 0 at those points. And it's not increasing forever, because if it was increasing forever, then 3 pi on 2 would have more y coordinates, or more z coordinates, which it doesn't. Let's do our peaks and troughs, so the maximum and minimum. Pi on 4, well, we think about this as our xy plane. X, we're starting here and we're going around this way. So this would be pi on 2, this would be pi, this would be 3 pi on 2, and that would be 2 pi. So pi on 4 would be roughly here, and we're going up to 1. So pi on 4, let's go up to 1. Let's look at our other maximum. So 5 pi on 4. 5 pi on 4, well, pi is here, so 5 pi on 4 would be out here. And we're going up to 1 again. Look at our minimums. 3 pi on 4, well, pi on 2 is here, pi is here, so 3 pi on 4 would be here. And we're going down by 1 this time. And we're going down by 1 over here. So the graph is going to go up, then it's going to go down. It's got to cross through this point first, then it's going to turn around, go down, then up to here, then it's going to go up to this point, and then come down to here, down to there, and then turn around and go there. So, it looks tricky, and you've got to imagine that's in 3D. It's kind of like a roller coaster that you might see at Luna Park or something, and it's going around. Yeah, and that's our graph there. I like these graphs, and once you understand that process, it's not that tricky. Okay. The last method is to graph, and if we're unfamiliar, well, the ones with sine, cos, and tan are easy because we know they're circles and they've got something to do with circles. But these ones are a bit trickier. Again, it's easy when it's sine and when z is equal to t, because that means it's going up at a consistent rate. When z is equal to t squared, it's not as straightforward. So another unusual curve, and when we're not sure what it looks like, one method is to draw at least 2 of the 2-dimensional curves, then combine them to create a 3-dimensional sketch. So we've got x is t, y is 2t, and z is t squared. Using x is t and y is 2t, we can rearrange to get y is 2x. Which means if we forget about the z for a second, if I'm looking just at the xy plane, so I'm looking at the graph from above, it's a straight line, y equals 2x. Don't care about the z's anymore. I'm standing up, I'm looking at the equation from above, and it's a straight line, y is 2x. That's one dimension. Let's do another one. Let's combine the x and the z. X is t, z is t squared. Rearrange, we get z is x squared. So if we're just in the xz plane, we don't care about y's. So we're just looking at xz, we don't care about our y's, just up and down and left and right, not front and back. If we do that, well, it's a parabola. So the shape when looked from above is a straight line, and when from looked to the right, it's a parabola. So we can convert our 2 lines into a 3-dimensional space. Remember that the first quadrant is now the bottom right, so the line y equals 2x looks a bit different. So that's our y equals 2x, and that is our parabola there. So what we have is a parabola, but the parabola is kind of being rotated so it's along the line y equals 2x. Because if we look it from the right, if we're just looking at it straight on, it looks like a parabola. If you've got a phone and you rotate it like that, when you're looking at it, you still see a flat phone. It's not, and you're thinking just 2-dimensional space, you still see a flat phone. If you're only in 2 dimensions and you turn the phone, you just see a flat phone. It looks a bit funny, but it's just a flat phone. Because in 2 dimensions, we don't have any depth. If I then look at this phone from above, and I'm looking from above, I just see a straight line. Again, I don't have any depth perception, so I just see a straight line. So if I'm looking at this parabola from above, it's a straight line. If you think about that, if you are a parabola and you go above the parabola, you just see a straight line. You can't see anything else. If we look at it to the side, we just see a parabola. It's going to look funny, but we just see a parabola. But it can't be a normal parabola, because if we looked at this parabola from above, it would just look like this, that line there. It wouldn't be y equals 2x, it would be the line y equals 0. So since it's the line y equals 2x and it looks like a parabola, it's going to be a parabola, but it's going to be kind of rotated along the line y equals 2x. So the black one would be our answer. So just a couple of hints, and I think I've spoke about this. Imagine you were a bird flying above the parabola. What would you see? A parabola? No, you would just see a straight line. If you were a plane flying above mountains that had no distinctive features, the Earth would look flat. So think about it logically. What do I look like in different dimensions? Right, and that is extension 2 vectors done. Thank you.